Welcome to Calculus Chat, a weekly discussion with your lecturers for 114. I'm Dr. Biggs, and here with me is Dr. Kellerman.
Hello.
And Professor van der Walt.
Hello.
Wow, we made it, guys. We have finished all the lectures for 114. We've handed in the last test, and we've handed in the last worksheet that is for marks. It's been quite a hectic semester.
Is every semester not quite hectic by the end of the semester?
In some ways, yes, but I do feel like there's something special extra hectic with this online teaching, which takes a little bit more effort. I don't remember being quite this exhausted when we were on campus still, but that was a long time ago, and one does tend to only remember the good and forget some of the bad.
Well, I can definitely tell you, setting a simple class test used to take me 15 minutes, and now it takes me a day or more.
Indeed.
Yes, and preparing an online lecture can easily take a half a day
Oh, yeah.
if you do it from scratch, but presenting a live lecture is maybe an hour's preparation and then an hour for the actual lecture.
Indeed.
But then the weeks when we don't have lectures, or when it's not our turn to do the lectures, then we have a bit of a break. So I think it kind of evens out.
Yes, no, I don't think it would have been manageable if all of us had to make all the video lectures.
Oh.
The only reason we're able to do it is because we divided it by 3.
This is the first time that I've been involved in a module that has 4 lectures per week, not the usual 2, and I must say it does dramatically increase the amount of work.
Yeah. Okay, so let's get into it. Well, what happened in our very last week of lectures? Well, we looked a little bit more deeply at indefinite integrals and really just the problem of looking at a wider array of functions to integrate. And we've really only covered the tip of the iceberg because there's so many methods and so many ways. However, we did dig a little bit deeper by going into transformations of the integral and looking at the method of substitution.
Yes, there are essentially 2 important integration techniques, and the others are all derivatives of these, not in the calculus sense, in the general usage. So the one important technique is substitution, and the other important technique is integration by parts. If you've got those 2, then you can do most things.
Which are doable.
Yes.
And integration by parts, I believe they will see next semester.
Yeah, they will. It's a pity there's not enough time in the first semester to include it in 114, but such is life.
When I was a student and we did substitutions, I remember feeling very uncomfortable when we would basically treat derivatives like fractions of differentials. So you would say u equals da-da-da, du over dx equals da-da-da, so du equals da-da-da dx. That bothered me a great deal.
Yes, I can attest to having the same concerns.
Yeah, I'm not a big fan of that notation, although it is completely rigorous if you interpret the dx and the du as measures,
Yes.
which they are, which don't worry if you don't know what that is. When you do your honors in mathematics, you'll find out.
Yeah, no, that's exactly the problem is that that's the most beautiful and simplest and elegant way of doing it and writing it out. But in order to make it rigorous, you need another 3 years of maths.
Yeah. So I prefer not to write it out like that, but I've bent to public opinion, to the opinion of James Stewart.
There we go. And tutorials, what can we say there? Well, it was a little bit quiet, but I think we still managed to have some good discussion, and we shouldn't be losing steam here towards the end. A lot of these questions are quite important for what's coming in the exam, and well, just in terms of mastering some of this beautiful material, and especially now that we're at a stage where so many things are being connected to one another.
Yes, and it's easy to kind of lose steam at the end and then not pay too much attention to the last work that's being done in a course, but that is a grave mistake. And I see this in a lot of courses, because I mean we don't just put anything in a course. We put the things there that are important.
Yeah.
right? And just because it's at the end doesn't mean it's less important. In fact, quite the opposite in this case. Integration is very important for going forward. It's a fundamental concept and it should be well understood.
Yeah, no, I mean, for me, I would say it's not uncommon to have some of the most important stuff at the end of the course, because that's when you get to the stage where you've built all the groundwork to actually make those statements that tie many areas together in one strong and important fact.
Absolutely.
Yes, many courses work up to an important result and then the course ends, and often that important result is right at the end of the course.
Yes, so don't rob yourself of the opportunity to enjoy some of the glory at the end.
I think the fundamental theorem of calculus, which comes just about at the end of 114, is a good example of that.
Yeah. Okay, so we are done with lectures, but we are not quite done with the course, right? So as we were saying, there's still a little bit to do. And specifically, I'm thinking of worksheet 15, where we've got an opportunity now to really master some of our skills coming from these last sections on integration.
Yes, Rory, you suggested a very nice question that combines optimization and integration, the very last question.
Oh, yes. Yeah, I hope our students will enjoy that, especially because there's a slight interactive element there to help you think about the problem. But I love it once you can start combining different areas together like that.
Part B of that question, the when I had a look at it, the algebra seemed quite messy, but it was remarkable how beautifully it all just cleaned itself up. All the terms just cancelled so nicely.
Indeed.
As I was doing the question, I suspected, gee, I wonder if this can even be solved analytically. But I just persisted, and the maths basically took care of itself. It was a very nice thing to see.
Yeah, so that's a good lesson to our students is sometimes maths does get messy, but you keep at it and it's your responsibility to make it simple.
So I was a first year student there in applied maths. I remember I had a solution involving mechanics, but it was an ugly, messy solution. And I asked the tutor, isn't there a nice, elegant way to do this? And he started laughing and he said, I'm afraid there isn't always a nice, elegant way to do maths. Sometimes it just is messy.
Indeed.
Well, that question, optimizing the integral, it's kind of a prototype of a whole branch of mathematics, variational analysis. The point of that whole theory is essentially optimizing an integral under some constraints on the function. So here, the constraints on the function is you've got a specific form of the function, which is determined by a parameter. But I mean, there are other kinds of constraints which makes it a lot more difficult.
Yeah, no, so I think we will have some hopefully good discussions still next week when we continue with tutorials. We'll still have Q&As, we still have feedback. So yes, let's put all our energy into making sure we really make the most of the opportunity of this last week to make sure we consolidate our understanding and master this last topic. And well, after that, we will truly be done with the body of the course. There will still be a little bit of tutor consultations and discussions on Discord as we prepare for the exams, but then the finish line is really in sight.
Is there any advice we can give for our students going into the exam?
Yeah, this is always a tricky one. For me, I mean, ideally, and this is the ideal situation, is you want to be in the position where you've already mastered the material, that you've really worked hard throughout the semester, so that once you get to the exam, all you really need to do is go back and refresh your memory on some aspects. But actually, you've already integrated that knowledge and the know how of how to do it in your mind, and you've got that understanding. But of course, this is not the situation all our students will find themselves in. So I would say, well, try and really identify any gaps that you have in your understanding. And a good place to look for such gaps are from the feedback you got in your tests and your semester tests. And make sure you try and patch those as good as you can.
Yes, I would advise not to study merely to pass WTW 114. Don't study in such a way that a week after the exam or a month after the exam you can't do the problems anymore. You've forgotten how to do those problems. Try and study in a way that you consolidate the ideas long term, because you will need them long term.
I mean, for me, after all, what are we here for? For me, I'm here to learn if I'm coming to university. That's the main reason you're here. And the certificate you get should just attest that, yes, you have learned. The goal is not the certificate, the goal is to have learned how to think and how to master some of these topics and ideas.
Yeah, one comes to university first to get an education and only then to get a qualification, not the other way around.
That's a good way of putting it.
And part of the learning that you're doing at university is learning how to learn.
Indeed. A skill that I think is becoming more and more valuable as time passes. The world is changing so fast that I think most places you'll have to be learning how to do things
Mm.
as you proceed in your life and in your career. It's not enough just to say, oh, I've spent my 3 years learning, now I have the knowledge, and the rest of my life I'm just applying the knowledge. No, this is a nonsense way of thinking.
Yes, with the exception of mathematics, which is a fairly stable subject. I don't foresee the foundations of mathematics changing anytime soon, but who knows? But with the exception of mathematics, I mean, a lot of times, especially in disciplines that are more geared more towards professional qualifications, the actual content that you've studied at university is probably out of date by the time you graduate.
Mhm.
But the fact that you've gone to university should mean that you are able, that you have now a solid sort of a theoretical foundation, and that you're able to absorb new knowledge and new skills quickly.
Exactly.
It's a bit like computer programming. There are so many programming languages which programmers have to constantly learn to use new languages, but if they understand the fundamentals of program design, then finding out what the exact commands are in each language is a relatively easy thing to do.
But the key word there that you used is understand.
Yes.
Right.
Yeah.
I think that's why mathematicians, besides being mathematicians and working at universities, are useful outside of university in the real world, is because our whole training is about understanding.
Hmm.
Like one of my professors used to say, mathematicians know that if they think about something long enough, they can understand it.
Yeah.
How long it takes, well, that depends on the mathematician and on the problem. But
Indeed.
the focus is on understanding, and then that makes assimilating new things easier.
So, any other general advice for our students entering into this exam period?
I think you should plan ahead for the exam period. You're going to have several exams over a relatively short period, like of 2 weeks.
Yes, so some of them might be right after one another.
Yes, right. You should plan ahead. Say, okay, right. I want to spend so many hours a day studying, and plan what you're going to study, when, based on your exam timetable, and based on how much work you need to cover in a particular module. And if you know that, oh well, there's something here that I need to pay a lot of attention to because I still don't understand it, then you should build this into your planning.
Yes, and I would say be realistic in your planning. Sometimes you can be a little too optimistic, thinking, "Oh, I'm just going to do all of this in this one day," but that backfires in bad ways. So be realistic and also take care of yourself. Right, make sure you give yourself a bit of breathing room, a few hours to take a break. Right, and that you allowing yourself to get some good sleep. We know the mind needs good sleep. If you neglect that aspect, you are setting yourself up for some disasters.
Make sure you get a solid 8 hours of sleep the day before an exam, because the extra 2 or 3 hours of studying or cramming that you're going to get in those last 2 or 3 hours is not worth the mental fatigue from not having had enough sleep.
Indeed.
Now, when you were doing matric, your end of your matric exams probably seemed like Mount Everest. And looking back at your matric exams, you now probably think that they weren't really that big a deal, or that was my experience. And so your first semester exams at this stage might seem daunting, but 6 months from now, you'll look back and in the bigger scheme of things, you'll realize these exams weren't that big a deal. So just place everything in perspective. In the bigger scheme of things, each individual exam isn't the make all or break all of your career.
Okay. And well, once our students manage to finish their exams and hopefully they are successful in completing their first semester, Well, what kind of maths do they have to look forward to in the coming semester and the next year?
Well, next semester in 1 to 4, there's some more calculus and the first bit of linear algebra, which is really nice.
Mm.
There's some Taylor polynomials, matrices, and there's a lot of beautiful mathematics in there.
And then there are some other smaller modules as well for students who are particularly doing maths or applied maths, right?
Well, the actuarial science students, they'll also be doing the numerical analysis course 1 to 3 with the maths and applied math students.
Aha.
And I think the mathematical statistics students, most of them do numerical analysis.
And that's basically where you use a computer to solve an equation that can't be solved analytically.
Yeah, or just to do it for approximation. Sometimes all you need, I mean, if we look at something like computer graphics, right? You need to, say, invert a matrix in order to do some transformation to display something. And there, it's not actually that important that you get the absolute 100% correct answer. What is much more important is that you are able to invert it very quickly, because if it's off by 1 pixel, that's probably fine and acceptable. It's not going to be a perceptible difference. But you want to be able to do it really fast so that you can have a good frame rate. So then I don't know, do they in the first numerical analysis already start looking at techniques of dealing with matrices?
I do think they do some systems of linear equations. I don't know if they do inverses. It's been a long time since I've done that course.
Aha. And hopefully they'll also do something like an approximation of an integral, right? We've already encountered integrals that we cannot integrate analytically, but like for the error function in statistics, it's important that we be able to approximate and get a good estimation of what those values are.
Yes, they do some numerical integration there. I think they do like Simpson's rule and the trapezium rule and things like that.
Aha.
But this error function, it's an interesting example, because so now we've got this integral which we need to be able to calculate for practical purposes, and we can't do this analytically. So now you can either use these numerical integration techniques, or a different approach is via Taylor polynomials,
Aha.
which is, I think, an example or an exercise in the 1 to 4 textbook where you use a Taylor polynomial to approximate the error function.
Wonderful.
On that topic, in this week's worksheet, there was a question that I thought was so nice. It gave a very nasty limit and asked you to find the limit using an integral. And the integral is basically a continuous object. The limit is basically, it was a limit in the variable n and another variable I, and those were discrete variables, 1, 2, 3, and so on. And I just found it fascinating that you could solve this basically discrete limit using a continuous integral. I think using Taylor polynomials to integrate is another example, beautiful example of using two seemingly unrelated ideas to solve new problems.
Yeah, and the reason why in this case you can connect these two unrelated things, the Taylor polynomial and the integral, is because of the fundamental theorem of calculus.
Mm-hmm.
Right, because the Taylor polynomial basically is a polynomial determined by the function values at a single point and the derivatives of the function at that point. And the fundamental theorem of calculus gives you a way to get past the integral, if I can put it that way.
So much beautiful stuff that lies ahead. So the other small module is dynamical systems, right? Where they also look at some first order differential equations.
Yes. My PhD student was last year a tutor for that module, and he started off studying physics before he moved over to mathematics. Such a wise decision. That's a joke, but anyway. Yes, and so he didn't take dynamical systems because the physics students don't have to. It's an elective for them, and he enjoyed it so much. He said it was such a beautiful module, and because you make relatively simple models, but still, you can see the behavior of how things are supposed to be there, even if it's not the best model.
Yeah.
It's really nice.
Now, I remember in my first year, at some stage, we did some dynamical systems, some basic ones. And I found it really fascinating when we got to the model for, when there's a murder and you want to determine how long the body has been murdered. And then there's this very simple differential equation that actually does a remarkably good job of describing how the temperature falls of the body. And so you can use that model then if you measure their temperature to determine, well, how long ago were they killed? A little macabre, but wow, that was beautiful stuff.
That's Newton's law of cooling, right?
Yeah.
Yeah, I think of Newton's law of cooling in the winter when my coffee cools down very quickly.
Okay, so that is next semester, but then there are plenty of new topics branching out to quite some different things also in the second year.
Yes, I mean, there's again, of course, a lot of calculus, but now it becomes more interesting, even more interesting,
Mhm.
where we move things up into more than one dimension.
Oh, yes.
And so now we're looking at functions of two variables, and then our graphs, instead of being curves in the plane, are surfaces in three-dimensional space. And then there's the theory of differentiation and of integration of these functions.
And then, of course, you can do things like optimize on two variables. And what if you have some interesting constraints? Ooh, fantastic stuff.
There'll be some more optimization techniques there in the second year multivariable calculus course. And some of the problems that we have been dealing with in 114 for when we're looking at optimization can also be dealt with these techniques. And it's quite interesting to note that one of the questions in the second year calculus semester test this year, which I happened to see, was exactly the same as one of the optimization problems we did in the lectures. Essentially the same. But they were solving it with a different technique.
Yeah,
Right? So many tools available.
beautiful stuff. Okay, so what else in second year? There's also a very solid course in analysis, 220, right?
Mhm.
And there we really get into the nitty gritty of how we build a mathematical theory. So that course, I would say, probably has very little, if any, new results that our students haven't seen. What it really is about is going back to some of the results, even the ones we've seen this year, like intermediate value theorem, and now building up the full reasoning for how we prove that from the ground, starting with what is a real number.
Yes, it's the foundations of calculus. But then that builds further on that. You build further beyond calculus. So it's not just the foundations of calculus. It's the foundations of analysis, which goes a long, long, long way in many different directions.
Then there's linear algebra, which I always found to be quite a beautiful area. And it's remarkable, actually, in how many places that gets applied. And it's quite different from just the sort of the calculus we do. It's a bit of a different language. I enjoy it.
Yes, it's interesting. So, at its heart, linear algebra can be viewed from, well, depending on your perspective. A central idea in linear algebra is solving systems of linear equations and the theory of systems of linear equations. So, do you have solutions? How many solutions? And so on. And this has a really fundamental application in the numerical analysis of partial differential equations, which are the almost all of mathematical physics uses partial differential equations as their mathematical models. And to solve these numerically, the techniques that they use boils down to solving enormous systems of linear equations, like thousands of variables and thousands of equations.
Yeah, no, so that's one huge application. The other one is, well, again, computer graphics is just filled with good linear algebra and doing all kinds of interesting transformations fast. I mean, even in my research on higher dimensional surfaces and connecting curves, one of the powerful techniques, while coming from calculus, is the idea of linearizing the system and then using linear algebra to learn more about what's going on with this more complicated curved object.
Hmm.
Yeah, I also, for me, one of the truly beautiful topics in linear algebra is the theory of vector spaces,
Aha.
just as algebraic structures. And for me, one of the epiphanies, mathematical epiphanies as an undergraduate student, was the notion of linear independence, which I just found to be such a mathematically beautiful and elegant property, a bit like epsilon delta characterizations of concepts in calculus. It's so simple yet so powerful, and it so beautifully captures the intuition of linear dependence, but in a mathematically rigorous way.
Hmm.
Now, I think one of my favorite results from linear algebra is the spectral theorem, which roughly says. So those of some of you will know already what matrices are, and it basically tells you that any matrix can be decomposed in a very nice way into very nice matrices.
Yeah, no. And once you get to the eigenvalues and eigenvectors, I mean, there's so much beautiful stuff there.
Yes.
Uh, so let's quickly just discuss what are some of the other good things. There's some more differential equations, a follow-up course, right, where you get a little bit more deeper. There's also discrete structures.
Now that's a nice course. They do a bit of recursion theory and they do some graph theory. Graph in the sense, not like we've been doing them in calculus, but a set of vertices with edges between them.
Mm-hmm.
If you've seen the movie Good Will Hunting, they have graphs, although the problems that they solve are not really cutting edge research problems, even though they make it look like that. But anyway, uh, they do a bit of number theory. Um, some students might find interesting the topic of cryptography, which is briefly touched on,
Mm-hmm.
some automata. It's a very nice course.
Yes, then there's also the vector analysis course, which contains some of the most beautiful results in undergraduate mathematics, which are higher dimensional versions of the fundamental theorem of calculus. And then when you see those theorems and you understand how they relate to the fundamental theorem of calculus we doing in 114, then you see how much of the structure is hidden by the fact that we're working in a one-dimensional setup. I mean, those results are just fantastic. Green's theorem and the divergence theorem.
Man, I am almost jealous of our students who get to experience all these beautiful topics still for the first time. It's like they get to read a book that I've already read. Now, you never get the opportunity to read it again for the first time.
Yeah. I want to maybe make one comment. So our students may feel that, well, they're doing first year math, and this must be so far removed from, mathematics at a research level, or advanced mathematics. Let me give them an example. So in 1 to 4, you're going to do the integration technique, which is integration by parts. Right. And it's a really basically like reverse engineered product rule for differentiation. So it seems quite innocuous, although it's quite powerful in terms of evaluating integrals. But now you say, well, evaluating integrals. So there is a French mathematician, well, I don't think he's alive anymore, Laurent Schwartz, who won the Fields Medal in the 1950s. Now, the Fields Medal is like the Nobel Prize for mathematics. And he won the Fields Medal for his theory of distributions, which is a very powerful tool for dealing with linear partial differential equations. Now, at its heart, fundamentally, the theory of distributions is integration by parts. Right? And this is a really advanced topic in mathematics, but it uses something that a first year student can do and can understand, and it uses it in a fundamental way.
Yeah, it's actually amazing how much really interesting and wonderful maths one can do just with what we've already covered and what you cover even just by second year. There are so many good areas of mathematics that you can already do impressively fantastic stuff, and like some of them might, in terms of solving a problem, might not need to go much beyond the tools that you've done by then.
Well, if you lived 200 years ago and you had the mathematical knowledge of a first year student, you would have been one of the leading mathematicians in the world. Bearing in mind that mathematics is thousands of years old, so it's actually chronologically a fair chunk of mathematics that the average first year student has already encountered based on how long mathematics has been around.
Hmm.
Indeed. So at this stage, seeing like this is our last episode for Calculus Chat, as we draw towards the end, I thought it might be nice to look a little bit back over the course and think about, well, what were maybe some of the things that we found unexpected, or what was something that really stood out to us, or that we had a lot of fun with?
What I found very rewarding was to witness the mathematical growth in many of our students, where at the start of the semester they couldn't really write a nice mathematical argument, and by now many of them do understand how to structure a mathematical argument in a rigorous way.
Indeed, I mean, for me, it's always a rewarding thing is to be interacting with engaged students who are here to learn and are really passionate about doing things. And for me, I mean, and I'm sure all of us, we partly you live off that energy. It's an interaction. We're not just one way transferring knowledge from our heads to you. No, it's an interaction. That's how our learning works. And in a way, I find it's a pity that we didn't have face-to-face interactions, because that really allows you to have more of those kinds of talks and little chats after class. But I think we did fairly well in finding some other ways of actually having those kinds of interactions, which were very rewarding.
Yes, I really enjoyed the kind of extracurricular mathematical discussions on Discord. Those were fun. And of course, the memes. I particularly enjoyed the Fibonacci.
Oh yeah, there were some fantastic memes. No, that was a lot of fun.
Yeah. It is also nice to see students on Discord and the other channels kind of not just sitting back and waiting for the tutors and for us to jump in, but getting engaged with each other, and assisting each other and explaining to each other.
Yes, and I mean, I think that is almost the best way to learn is, well, to teach, is to try and explain it to somebody else. It really forces you to make that idea very clear in your mind. And then, of course, I had a lot of fun with the calculus chat. I think the three of us had some fantastic conversations, almost better than what I expected. This was fun, and I hope our students very much enjoyed it.
I also enjoyed the calculus chat and was also surprised about how well it went, doing it online. So kudos to you, Rory, for your excellent editing.
Shh, it's unedited.
Yeah.
We just naturally such good conversationalists.
Yes.
Well, that's all, folks, for 114. Please take care of yourself in these scary times.
And good luck with your exams. Keep calm and carry on doing calculus.
Woohoo! Cheerio!
Bye.
Goodbye.